Good morning, students. I am Suneetha, Assistant Professor of Chemistry from Kakatiya Government College, Hanamkonda. Today we are going to discuss about aromatic hydrocarbons. Then our subtopic here is orientation of aromatic substitution. Orientation of aromatic substitution. So what is meant by orientation? Let's see. Orientation. Already present group in the benzene ring which decides the incoming electrophile to occupy a particular position, and the rate of the reaction is also decided by the particular benzene. And this phenomena is called orientation. So whenever a substituted benzene, if it is subjected to electrophilic substitution once again, then the already present substituent, it decides the position of the incoming electrophile. And to some extent, the rate of the reaction is also affected by already present electrophile in the benzene ring. And this is known as orientation. Now, there are two types of the groups. Let us consider those groups. If we consider monosubstituted benzene, that is already one electrophile is present on the benzene ring, the rest of the 5 positions are available for electrophilic substitution. So this electrophile which is already present in the benzene ring, which decides the position of the incoming electrophile, that is only known as orientation, and this orientation is of two types. Two types of groups are present which decide the position of the incoming electrophile in the case of monosubstituted benzene. Now, let us see the positions in the benzene ring. Here, this is the group which is already present. That's the electrophile which is already present. This is monosubstituted benzene. So, let's say the numbering of carbon atoms in the benzene ring. This is clockwise direction numbering 1, 2, 3, 4, 5, 6. And these positions can also be written like this. This is first position. The adjacent position to one position is known as ortho position. So 1 and 2 ortho, 1 and 6 ortho. Okay. Now 1 and 2 or 1 and 6 ortho. Right. See here 2, 6 positions are ortho positions denoted by O. That is when compared to 1, this 2 is ortho. When compared to 1, the 6 is ortho. Therefore, 2 and 6 positions are ortho positions. This is 3 and this is 5. These are meta positions. 3, 5 positions are meta positions denoted by small m. Next, this one, fourth position when compared to with respect to this group. Okay, this group is present on the first carbon with respect to this carbon. The fourth position is a position denoted by P. So, in monosubstituted benzene, the different positions here we discussed. So, this is when this is 1, that is the carbon to which the group is attached, that is first carbon, and second and sixth carbons are ortho positions, third and fifth positions are called meta positions, and fourth position is known as para position. Okay, so these are the 3 different positions we come across which are available for the in these monosubstituted benzenes. Okay, now let us see the groups. Here, 2 types of groups are present. 2 types of groups. The first one is electron releasing groups or ortho para directing groups. Electron releasing groups are ortho-para directing groups. Okay. Second one is ring activating groups. Electron releasing groups are ortho-para directing groups, also known as ring activating groups. Okay. Ring activating groups. So electron releasing groups are ortho-para directing groups or ring activating groups. This is one type of the groups we come across. And second type is electron withdrawing groups. Electron withdrawing groups are meta-directing groups are deactivating groups. Deactivating groups, it should be groups. Okay. So there are two types of the groups. We consider there. The first one is electron releasing group. Second one is electron withdrawing groups. Electron releasing groups are ortho-para directing groups or ring activating groups, and electron withdrawing groups are meta directing groups, or which are also called ring deactivating groups. Now, first of all, let's discuss about the first type of the groups, that is electron releasing groups or ortho-para directing groups. That is, these are the groups direct the incoming electrophile to ortho and para positions. Okay, so these are also ring activating groups. That is, they increase the activity of the benzene ring activating groups. They increase the reactivity of the benzene ring. Thus, the incoming electrophile easily attacks this ortho and para positions. So, this is about the first type of groups, that is electron releasing groups or ring activating groups or ortho-para directing groups. Now let's discuss about the first type of the groups first. Now let us see here. Ortho-para directing groups, which are called electron releasing groups or ring activating groups. So the electron releasing or electron donating element or the group of elements will increase the electron density in the benzene ring. This is called ring activation. So electron density of the benzene ring activity of benzene ring is increased due to a greater electron density in the benzene ring due to the presence of electron donating or releasing atom or group of atoms. Atom or group of atoms are the species. Electron donating or releasing species will increase the electron density in the benzene ring. Okay, the benzene ring. Now let us see. The effect of substituents will increase the electron density in the ortho and para positions. That is, in the 2 and 6 positions, the electron density will be increased due to the presence of electron releasing groups. And the effect of substituents will increase the electron density in ortho para positions and para positions. So, the incoming electrophile will be directed to ortho para positions by the already present groups in the benzene ring. Okay, so the already present group which directs the incoming electrophile to ortho and para positions. Okay, that's why these groups are called ortho-para directing groups, and high electron density in ortho and para position will ease the attack of the electrophile, so increasing the rate of the reaction. These groups, they also increase the rate of the reaction by increasing the electron density in the benzene. So electron donating group activates the ring and also called activating groups. Now here, let me correct this. See this one. The effect of substituents will increase the electron density in the ortho and para positions. Okay, ortho and para positions here. Ortho is 2 and 6 position and para position is 4th position. So whenever the electron releasing group is present already in the benzene ring, it increases the electron density in the ortho positions, that is 2 and 6 positions, and para position, that is 4th position. So the newly coming electrophile, it has to go to either ortho or para positions, ortho and para positions, as the electron density in those positions is high. And in this regard, these groups also increase the ease of the attack of the electrophile, and at the same time they increase the rate of the reaction also. Therefore, these electron donating groups, they activate the ring, and they are also called ring activating groups. Ring activating groups. And releasing groups are ring activating groups. What they will do? They donate or they release the electrons into the benzene ring at ortho and para positions. There the electron density will be increased. So the newly coming electrophile is positively charged or electron deficient molecule. We know. Therefore, it has to go to these positions only, that is ortho and para positions. Because of this reason, they decide the position of the incoming electrophile, and at the same time, as they release or donate electrons to the reaction increases. The rate of the reaction increases, and these groups are also called ring activating groups. Now, what are the examples of ring activating groups? Let us see. We can observe here. This one, OH ring activating group, Cl ring activating group. This is a NH2 group, amino group. This is COCH3 group, COCH3 group. This is acyl group, and this is methyl group or R group, alkyl group, C2H5, CH3, etc. Hydroxy group, chloride, that is halogen. This is NH2 group, acyl group, COCH3, and methyl group. These are the groups which increase the electron density in the benzene ring, and they activate the ring. So the rate of the reaction increases. And these groups, they direct the incoming electrophile to ortho and para positions only. Okay. Let us see how they activate the benzene ring. Okay, in this mechanism. See this? This is monosubstituted benzene. Monosubstituted benzene. That is the benzene ring which has already an electrophile on it in one position. Let me say. Okay. Then what happens? As these are electron releasing groups, this Z is electron releasing group. It releases electron density. Okay. It pushes this electron pair, which is present on this. Okay. Towards this carbon. Okay, then what happens? Then what happens? This Z becomes positive. Okay, this Z becomes positive, and here a double bond will be there, and this pair of electrons, they move towards the adjacent carbon. So a negative charge will be generated on this carbon. Okay. A negative charge will be generated on this carbon. When there is negative charge, either negative charge is present on the carbon, this electrophile, it goes and attacks that particular position only. Electrophile has to go to that particular position only. And let us see the negative charge on the other positions also. If this negative charge, this pair of negative charge is nothing but a pair of electrons, they move inside, then this pair of electrons, they move towards this carbon, then this para position, it gets negative charge, therefore electrophile easily goes and attacks this position. Okay, the other way, this negative charge, it moves inside, this pair of electrons, they move towards this ortho position, then here also negative charge will be there, their electrophile can go and attack this carbon. So whenever electron releasing group is present on the benzene chain, as the first is substituted, then what happens? The electron density will be increased on two ortho positions and one para position. So the incoming electrophile, the second electrophile, it has to go to either these ortho and para positions only. Ortho and para positions only. Okay, that we can show here. Negative charge we have shown on this carbon, negative charge here, negative charge. Only meta positions, no negative charge. Okay, so here this is negative charge. And this carbon, attack of electrophile we have shown here. Electrophile, it is forming a bond here. This new sigma bond is formed here. Then afterwards, it loses this proton, this carbon, to regain its aromaticity. thus a substituted product is formed. So it is a di-substituted product. This is mono-substituted product, which is subjected to electrophilic substitution. Then a di-substituted product is obtained. Okay, this is substitution at ortho position. Ortho, either here or this side, we can say it is ortho. So ortho. And next, para position. If this electrophile goes to this carbon, here the electrophile forms a new sigma bond with this para, the fourth carbon. Then what happens? This proton, this carbon gets positive charge. Adjacent carbon gets positive charge as it is having 4 bonds, and this will be having 3 bonds. It gets positive charge. And what happens? It loses this sp3 carbon. It loses proton to regain its aromaticity. Thus, a substituted product is obtained. This is one substitution. Therefore, when with respect to first position at fourth carbon, the electrophile is substituted. Therefore, it is para disubstitution. This is ortho disubstituted product. So, whenever this electron releasing groups like OH or Cl or NH2 or COCH3 and CH3 etc. are present, then what happens? In ortho and para positions, the electron density will be increased. Thus, we get a disubstituted product in ortho and para positions. Okay, and here about this chlorine we will talk later, because it is an electron releasing group, but it is a meta directing group. Okay, that we have to remember. Now here other examples we have given for electron releasing groups. NH2 group, NHR. This is NH2 is primary amine, NHR is secondary amine, NR2 is NH NH2 primary, this is NHR secondary amine, this is tertiary amine, and this is hydroxyl group, this is alkoxy group, this is ethyl group, this is ethyl group, this is phenyl group. So the first four are, these are the first 4 and 5, these are the strong electron releasing groups, and these are the weak electron releasing groups. So this is about ortho-para directing groups, and in this case what happens we have discussed. Okay, so now let's discuss this ortho-para directing ring activating groups activity with one specific example. Okay, one specific examples. Let's consider one amino or methyl group etc. And explain the formation of ortho and para disubstituted products. Okay, let us see. So these are all the examples for ortho-para directing groups. Now let us consider one of these groups and explain how it directs the ortho and para positions. Now here we are considering amino group as the first substituent on the benzene ring. Okay, so amino group is NH2. This one, NH2 group. Now the non-bonded electrons present on the nitrogen in amino group, that is this electron pair, okay, will be donated to benzene ring. It is donated towards benzene ring. So nitrogen will become positively charged and the negative charge will circulate in the ring. Negative charge will circulate in the ring. So different resonance structures shows ortho and para positions are rich in electrons, attracting electrophilic attack. Okay, so positive inductive effect, that is plus high effect, and positive mesomeric effect, that is plus m effect, okay, will make amino group electron releasing group or ortho para directing group. So I will explain this with the help of this structures. Okay, now let's consider this. This is aniline amino benzene. This is amino group which is present on the benzene ring. This is called aniline. It's the uh, name given to this particular substance, aniline, aniline, aniline. When this aniline, it is subjected to electrophilic attack. Then what happens? Let's see. If this electrophile attacks on the ortho position, this ortho position, what happens? Let us say in this resonance structures. Ortho attack. Electrophile goes and attacks this carbon. It utilizes electrons to form a sigma bond between this electrophile and this carbon. See, electrophile and carbon in new sigma bond is formed with the help of this pair of electrons, that is this pair of electrons. Okay. Then what happens? This pi bond electrons utilized in the bond formation with this electrophile. Then this particular carbon which is adjacent to this carbon, it gets positive. And this positive charge is in resonance with the remaining two pi bonds in the benzene ring. So this pi electrons, they transfer towards this carbon. Therefore, this positive charge disappears from this carbon and positive charge is obtained on this carbon. You can see here. Okay. Now shift of a pair of electron, that is this pi bond electrons towards this bond takes place. Okay. This bond takes place. Then the positive charge is on this carbon and this carbon gets the positive charge. You can see here. Okay. So like this, these are all the resonance structures. These are all the resonance structures obtained when the electrophile attacks on the ortho position. Ortho position. Okay. Now, in the next step, what happens? These are all called sigma complex. Sigma complex. So this sigma complex, it loses this proton from this sp3 carbon. See, loss of proton. This bond pair, it goes inside, and this double bond present in between this N and H, this pi bond electrons gets transferred towards nitrogen. Therefore, the positive charge on nitrogen electrophile at ortho position to this amino group. Okay, this is attack of electrophile at ortho position. Attack of electrophile at ortho position. Right? Now, let us see. So, in this ortho attack, we have 1, 2, 3, 4 resonance structures, and here this in ortho attack, more number of resonance structures are produced. And electrons present on nitrogen are also in body resonance. Therefore, this is more stable, and we get the final product here. And when electrophile it goes and attacks this meta attack, what happens? This electrophile goes and attacks this meta carbon, that is third position, to the first. Then what happens? Let's see. So this electrophile forms a bond with this, with the help of this pi bond electrons with this third carbon. See, sigma bond is formed in between carbon and electrophile, and this carbon which is adjacent to this carbon, that is sp3 carbon, gets a positive charge here. Okay. Now this positive charge is delocalized with the two other uh, pi bonds present in the benzene ring. Thus this structure and this structure we get, and in this the electrons present on nitrogen atom are not involved in resonance. Therefore, here we get only three resonance structures. Here we get only these three resonance structures. And finally, this sigma complex, it loses a proton to form the disubstituted product, that is meta disubstituted product. It is attacking the carbon, and we get a meta disubstituted product here. Now next one, let's say the para attack. When this electrophile goes to this para carbon, that is fourth carbon, then what happens? This electrophile With the help of this pair of electrons or this pi bond electrons, it forms a bond with this para carbon. See, a sigma bond is formed in between this fourth carbon and electrophile, and the adjacent carbon, it gets the positive charge, and this positive charge is in relocalization with the two other pi bonds present in the benzene ring. Okay, so here this pair of electrons, they move towards this carbon. Then what happens, this carbon, that is first carbon, gets the positive charge, and the positive charge present on the first carbon is delocalized with the help of the pair of electrons present on nitrogen atom. Therefore here we get a double bond. Okay, double bond. Nitrogen gets the positive charge. Next, what happens, these electrons move towards these two carbon atoms, and these pi bond electrons move towards nitrogen. Thus we get this structure. Here it should be single one, okay, because the bond pair moves towards this nitrogen, so it should be a single bond. Now what happens here, this, due to shift of a pair of electrons towards these two carbon atoms, in between these two carbon atoms, this carbon gets the positive charge, you can see here. Okay, now what happens, this sp3 carbon, it loses a proton to the other part of the reagent, that is negative part of the reagent, to form a pi bond here in between these two carbon atoms, that it regains the aromaticity, the benzene ring regains its aromaticity, and finally we get the 1,4 disubstituted benzene, that is para disubstituted benzene. Also, we have more number of resonance structures, you can see here, more number of resonance structures like ortho attack. So greater the number of resonance structures, greater is the stability, and that will be easily formed. So in the meta attack, number of resonance structures are less, and the electrons present on nitrogen atom are not involved in resonance. Therefore, it is less stable when compared to ortho and para attack. So here, these are the more stable intermediates produced in ortho and para attack. Therefore, when amino group is present on the benzene ring initially, it directs the incoming electrophile to either ortho or para positions, forming ortho and para disubstituted products. Okay. Now, see here. More resonance structures are possible for ortho and para positions, just now I said, okay, for the attack of electrophile than meta positions. So in the meta positions, number of resonance structures are less. When the second electrophile, it attacks meta position, the number of resonance structures are less when compared to ortho and para position attack, okay. So as nitrogen is plus I and plus M group, that is, it releases electrons towards the adjacent carbon. Structure with nitrogen as positive charge are stable in ortho and para resonance structures. I will show you this one. This structure with the nitrogen with the plus charge, and in this structure nitrogen with the plus charge. So stable we wrote here. Okay, yes, stable. Okay, right. So the structures with the nitrogen as positive charge are stable in ortho and para resonance structures. Such nitrogen positive charge structure is not formed in the meta attack and unstable. So in the meta attack, we cannot see such type of UC. In this, in these structures, nitrogen with positive charge, such type of structure is not there. Okay. So the meta attack, such type of structure is not formed in the meta attack, and therefore it is unstable. Hence, amines are ortho and para directing groups. Okay. So here in ortho attack, this is one of the resonance structures where nitrogen bears the positive charge. Then para attack, this is one of the resonance structures where nitrogen bears the positive charge. Okay, so these are the stable forms. Therefore, the ortho and para attack is more favored in the case of amino group when it is present as a first substituent on the benzene ring. Okay. Right. Now, second example, let's consider, that is methoxy group. Methoxy group, OMER-OCH3 group. Okay, methoxy group when it is present on benzene ring as a first substituent. So how it will influence the next electrophile, that let us discuss here. So methoxy group is Ortho and para directing group. Okay. Methoxy group is ortho and para directing group. Like amino group, and oxygen atom attached to the benzene ring has this one. Oxygen atom attached to the benzene ring has lone pair of electrons. So due to which plus M effect, that is, it is electron releasing group. Plus M effect means it releases electrons towards the adjacent CC bar. So due to this plus M effect, different resonance structures are possible. You can see here. This is methoxybenzene, where methoxy group is the first substituent present on the benzene ring. So this pair of electrons present on the lone pair of electrons present on the oxygen atom is shifted towards this bond, O and C bond. Then what happens? A double bond is formed in between this carbon, ring carbon, and oxygen. Oxygen bears the positive charge, and this pair of electrons shifts towards this carbon, where this ortho carbon, it has negative charge. Now resonance structures shift of this negative charge towards this side inside, then this pair of electrons moves towards this carbon, that is para carbon also getting negative charge. Okay, the next resonance structure, what happens? This pair of electron move inside, and the pi bond electrons moves towards this carbon, then this ortho carbon, it gets negative charge. So in these structures, due to plus M effect of this alkoxy group or oxygen atom of alkoxy or methoxy group, the ortho their negative charge we can observe. So wherever the negative charge is present, are then towards that particular carbon, electrophile goes and attacks. Therefore, electrophilic attack will be at ortho and para positions. Okay, so this is the first structure. Once again, we get these are the resonance structures obtained from methoxybenzene due to plus M effect of oxygen present in methoxy group. Let's see. Positively charged oxygen will be stabilized by the plus I effect of methyl group. Oxygen is resonance structures. Oxygen is positively charged, and this positive charge on this oxygen is stabilized by the plus I effect of, that is electron releasing effect of methyl group. Methyl group, this group, it releases electrons towards oxygen, therefore this positive charge is stabilized. Okay, plus I effect of methyl group. Okay, and the combination of mesomeric effect, that is mesomeric effect of oxygen, and inductive effect, that is I effect of methyl group, makes methoxy group 2 act as ortho and para directing or ring activating group. Even the oxygen atom is in positive charge, that is minus I group, but this methoxy group is ring activating group and ortho para directing group due to plus M effect of oxygen and plus I effect of methoxy group. This becomes ring activating group, that is methoxy group becomes ring activating group, and it directs the incoming electrophile to go to either ortho or para, and ortho and para positions only. Now let us show the different structures where the electrophile attacks ortho, meta and para positions of this methoxybenzene. Methoxybenzene. What is this ortho effect? Ortho attack. Ortho attack. This electrophile, it goes and attacks this carbon. Okay. With the help of this pair of electrons or pi bond electrons, it forms a sigma bond with electrophile, and the adjacent carbon suffers with a positive charge. Then this positive charge in delocalization with the remaining two electrons, two pi bonds present in the benzene ring. So we get two different two other, let me say, two other resonance structures. Okay, now finally the positive charge present on this carbon atom is also stabilized by the lone pair present on the oxygen. Okay, then we will get this structure which is more stable, where oxygen is having a positive charge and the lone pair present on oxygen is also involved in the delocalization of the positive charge on the carbon of benzene ring. Thus, finally, what happens? This carbon, where electrophile is attacked, that is sp3 carbon, it loses a proton to the negative part of the reagent to form finally the ortho substitute, ortho disubstituted product. Okay, so here it has more number of resonance structures, where more stable resonance structure is present here. And the positive charge on this oxygen is also stabilized by this methyl group, which is electron releasing group. So due to the presence of plus I effect of this methyl group and plus M effect of this oxygen, this methoxy group has become ortho and para directing group. Okay, now let's consider the meta attack. Meta attack, that is, this electrophile, if it attacks the meta position, then what happens? Let us see. So in the meta position, if it attacks, the bond is formed in between this carbon and the electrophile, and this carbon is sp3 carbon. There should not be this pi bond. Okay, it should not be there. Then what happens? This adjacent carbon gets the positive charge. Okay, now this positive charge is in resonance with two other pi bonds present in the benzene ring, that is delocalization of the positive charge takes place. Therefore, the positive charge, we get the different resonance structures, where positive charge is present on this carbon, and in the other structure positive charge is present on this carbon also. Okay, and finally oxygen, the electrons present on oxygen are not involved in the resonance. Okay, and we get only three resonance structures here, and finally we get a substituted product due to loss of proton from this sp3 carbon. So this benzene ring regains its aromaticity and we get a meta disubstituted product, where number of resonance structures are less, therefore it is less stable. And let's consider the para attack. This para attack, what happens? Electrophile goes to para carbon, that is fourth carbon, and attacks, and it, with the help of this pi bond electrons, it forms a sigma bond with this electrophile, and a new sigma bond is formed. This carbon becomes sp3 carbon, and the adjacent carbon gets the positive charge, as it has only three bonds surrounding it. Then what happens? This positive charge is delocalized with the help of two other pi bonds present in the ring, and the other carbons, they get the positive charge. Here, this shift of these electrons towards these two carbons, this carbon gets the positive charge, which is stabilized. This one, this is stabilized or delocalized by the electron pair present on oxygen. Therefore, a pi bond is formed in two bonds. Double bond is formed in between oxygen and carbon, and oxygen suffers with a positive charge. And this positive charge on oxygen is delocalized by the electron releasing nature or plus I effect of methyl group. The next step, what happens? This pi bond moves towards these two carbons. So this pi bond electrons moves towards oxygen, and this carbon gets the positive charge. You can see here. And finally, this sigma complex, it loses proton, that is a hydrogen atom without electrons. Okay, and then what happens? This pair, it goes inside, and the final product is obtained as a paradise substituted product, which it regains its aromaticity, that is three pi bonds are present. And in the first attack, that is ortho attack, and here in the para attack, we can see more number of resonance structures, and here oxygen bears the positive charge. In this also oxygen bears the positive charge. These are the stable structures. Therefore, whenever methoxy group is present on the benzene ring, it directs the incoming electrophile to either ortho position or para position. Okay, whereas in the case of meta position attack, what happens? Number of resonance structures are less, oxygen electron pairs are not involved in resonance, therefore this is less stable, and ortho and para more stable forms are present, therefore they are only forming ortho and para disubstituted products. Okay. Now, let's see. Okay. For the attack of electrophile, then meta position we have discussed, and oxygen is plus I and the plus M group, and methyl group attached to oxygen being plus I group. It, the structures oxygen as positive charge are stable in ortho and para resonance structures. We have discussed already here in ortho and para the structures in which oxygen bears a positive charge are stable. Okay, stable. Uh, they are formed in the case of meta attack. Such oxygen atom with positive charge resonance structures are not formed, and they prove meta attack as unstable. Ortho and para directing group are ring activating group. Okay. Now, last example. This is alkyl group. When alkyl group is present as a first substituent on the benzene ring, how it will influence the incoming electrophile. Okay, that let's discuss. Alkyl group, that is R group, or here specific example dash CH3, that is methyl group. Alkyl groups, they are also ortho and para directing groups, but these are weak activating groups. They are not like strong activating groups like methoxy group, amino group, or acyl group, etc. But these are the weak ortho para directing groups. Okay. They are weak ring activating groups. Plus I effect and hyperconjugation stabilize the resonance structures. Plus I effect and hyperconjugation of methyl group, it stabilizes the resonance structures. Thus, ortho and para substituted product is obtained whenever methyl or alkyl group is present as a first substituent on the benzene ring. Now, let us see the different uh, structures, resonance structures obtained by the ortho, meta, and para attack of electrophile and benzene ring. Okay, now here. First one, ortho attack at this carbon with the help of this pair of electrons, that is pi bond electrons. A bond is formed in between electrophile, and sigma bond is formed in between electrophile and this particular carbon, that is ortho carbon. Okay, then this carbon, it gets the positive charge. Mm. Orientation of the pi bonds is different. Okay, this carbon gets the positive charge. Then this positive charge is stabilized by the resonance due to the remaining two pi bonds present in the benzene ring. These two pi bonds, this pi and positive charge is localized by the resonance due to two other pi bonds present in the benzene ring. You can see here. Then what happens? We will get different resonance structures where positive charge is delocalized throughout the ring. Okay. Uh, Now, finally, this resonance, that is sigma complex, it loses this proton. Then we get ortho disubstituted product. Ortho disubstituted product. Okay. In this, the positive charge should be here, not here, because it is already having other bonds. Right. Or this pi bond should be here, then positive charge. This is correct. Positive charge should be here only, and pi bond must be there. Okay. So here, shift of pi bond towards this carbon takes place. That we did not show. Right. Pi bond should be here in between these two carbons, then positive charge on the adjacent carbon. If this carbon is the carbon loses a proton, then a pi bond is formed in between these two carbons and it loses its positive charge. Finally, we get ortho disubstituted product. Okay. This is ortho attack. Now let us see the para attack. In para attack also what happens? The electrophile goes and attacks the para carbon and the adjacent carbon gets the positive charge, and this positive charge is delocalized. See, delocalized here, here, and here. Okay, let's see. Positive charge is delocalized with the help of the other two other pi bonds present in the benzene ring. And finally, the sp3 carbon, where the electrophile is present, loses a proton to form the para disubstituted product. This is para attack. Now let us see the meta attack. The meta attack, what is that happening? See, this is the meta carbon and third carbon, where electrophile is forming a bond, and the distant carbon gets a positive charge. This is stabilized by resonance, and here this, due to shift of electrons towards these two carbons, this carbon gets the positive charge, we can observe here, and this pair of electrons move towards these two carbons, then this carbon gets a positive charge, and now this sigma complex, it loses a proton to form the substituted product, that is meta substituted product. Okay, now in this uh, let us see the structures. So more resonance structures are possible for ortho and para positions. More number of resonance structures are possible for, what do you say, ortho and para positions for the attack of electrophile than meta position. And see this one. Here, the structure with methyl bearing carbon with positive charge are more stable. Let me show this. Here, this one, stable, we wrote. The structure with the methyl bearing carbon, where the carbon to which methyl group is attached, this carbon is bearing a positive charge. This structure is more stable. And this type of structure is present only in this ortho attack and para attack. You can see in ortho and para attack. So this is stable structure, and here stable structure, where the positive charge is present on the carbon to which methyl group is attached. Because methyl group is electron releasing group, it stabilizes this particular positive, it delocalizes this positive charge with, because it is a electron releasing group or plus height group. So such type of structures are present only in ortho and para attack, whereas such type of structure is not present in meta attack. You can see this carbon is not having positive charge in any of these structures. Okay, so here it is there and here it is there. Therefore, these two are stable structures. Now here, so the structure with methyl bearing carbon with positive charge are more stable, because methyl group is plus height group, that is positive inductive effect group. Okay, and stabilizes the structure by releasing the electrons. So in ortho attack and para attack, such structures are formed, but not in meta attack. That's why ortho and para positions of toluene, that is methyl benzene is also called toluene, undergoes electrophilic substitution than at meta. Okay, so toluene, it directs, that is the methyl group present on benzene ring, it directs the incoming electrophile to ortho and para positions only, but not at meta. So we get ortho and para disubstituted product only. Now let's see the few questions which are related to today's topic. Okay, there the first one is, what is meant by activation of benzene ring? Explain with an example. Just now we have discussed methyl group, amino group, methoxy group. These are all ring activating groups. And which one of the following gives ortho and para halogen substituted products? Explain with mechanism. Whether nitrobenzene or methyl benzene. So nitrobenzene, nitro group is meta these two, methyl benzene gives ortho and para halogen substituted products. So in the case of electrophile, if we write Cl plus, we will get ortho and meta ortho and para chloro toluene as the product. So methyl benzene, it gives ortho and para halogen substituted products from these two. Okay. Now next one is, name 4 strong ortho para directing groups. Amino group, hydroxyl group, methoxy group, acyl group, alkyl group. These are all strong orthopara directing groups. Give one reaction of electrophilic substitution for each. So we have already discussed methoxy group, aniline, and methyl group, like that we can give the examples. Next, discuss electrophilic substitution of aniline. Just now we have discussed electrophilic substitution of aniline. Aniline is aminobenzene. Aminobenzene is ortho-para-directing groups. Electrophilic substitution we have already discussed. Okay. Next one, explain the orienting influence of halogen in chlorobenzene. So chlorobenzene, the halogen atom, how it influences the incoming electrophile, that we should write here. Okay. Now, thank you. We will stop here. I'll continue with the meta directing groups in the next session. Thank you once again, all of you.